circles, each centered at the origin with a different radius, okay? And look at the red arrows. These are a useful tool to indicate in the plane which is the direction of growth of our two variable functions, okay? This is a way to represent the two variable functions together with these red arrows, because I have the level sets and the directions of growth. If I move from the inner circles to the outer circles, in this case, I increase the level of my function because it is a positive definite quadratic form like this. Okay? So the smaller circle is when c is equal to 0, which is a point basically. Okay? That if I move away from the center here, I increase the value of my quadratic form, right? So this is one example. Here is another example, 100 minus x squared minus y squared. Now remember, it's a constant minus the previous one. So this is concave. This is like this, okay? Clearly. It starts from 100 and it goes down, but it is a quadratic form as well, plus a constant. If I impose equal to c, then I have x squared plus y squared is equal to 100 minus c. So by increasing c, the arrows, the direction of growth goes towards the center because it is like this. So if I move from outside circles to inner circles, I increase the value of my function. Is that clear? So this is an alternative way to represent a two variable function, which is similar to, the so-called, I don't know how to call them, you know, this line in maps, geographic maps, these lines that indicate the same height. It's called ISO something. I don't remember the name. It's called, but it is the same. They are level curves, basically. Okay. If you move along these lines, you don't change your height. Okay. Okay. So this is the basic. So what is the problem with these curves? Now this is another example. The Cobb-Douglas production function. What are the level curves of the Cobb-Douglas production function? Y is equal to f of x1, x2, or KL as this representation in the space. Okay? If you imagine to cut this surface with planes that are parallel to the base plane KL, you get this set of level curves. Okay? And if you move from towards the outside, this direction, you increase the level of the output. Okay? So for instance, if you remain on this level curve, the level of the output will be C3. But you can obtain C3 either with high level of labors and either with high levels of labor and low levels of capital, or with alternative production combinations with lower levels of labor and higher levels of capital. Okay? These are the combinations of the two input factors, labor and capital, giving the same level of output. And typically, the shape of these level curves for production functions, which are called isoquants, are like this. They are decreasing and convex functions. While this is, in the typical case, it is concave, you see? In the typical case, because it can also be quasi-concave. It is concave when the sum of the exponents is less than 1 or equal to 1, but can also be larger than 1. It is no longer concave, but it has the level set similar to this one, qualitatively, okay? It's called quasi-concavity. I will show you with some numerical examples that this is actually the case, even when the sum of the exponents is not larger than 1. It's not smaller than 1. For instance, suppose that you want to have this general Cobb-Douglas production function in two variables. What are the level curves at height z0? So you fix a given level c, which we call z0, because z is the name of the third variable. It's a given level z0. I should write capital A times x to the power of alpha times y to the power of beta equal to z0, okay? Here, alpha and beta, in this case, I don't impose any restrictions. can be smaller than 1, there are some, can also be larger than 1, okay? This is a way to write the equation of the level curves implicitly, okay? A function of x and y equal to a constant. Alternatively, I could write a function of x and y equal to 0. Why? Because if I move this on the left, it is a x to the power of alpha, y to the power of beta minus z0 equal to 0, which is again a function of x and y equal to 0, okay? So having a constant here, or having 0 because the constant has been moved to the left, is exactly the same for our computations, okay? And this is the implicit form. But now I could be, in some cases, I would like to make this explicit with respect to y regarded as a function of x, or alternatively, x regarded as a function of y, which means solving this for y or for x. Very typically, I want to solve this for y, because x is the independent variable, y is the dependent variable. If I solve this for y, I have to write this, y to the power of beta is z0 over capital A times x to the power of minus alpha. Remember that these are positive quantities. So y is this constant, z0 over A to the power of 1 over beta times x to the power of minus alpha over beta. And this is independent of whether these have a sum which is less than 1 or larger than 1, so independent of whether our function is concave or not, okay? We have the same shape of the level set, which is an elementary power function in one variable with a negative exponent. And this means that the qualitative shape of our level curves is like this. So the qualitative shape is independent on whether the size of these coefficients, okay? It is always like this, and z increases by moving from inner level curves to outer level curves, okay? You will see that this shape of the level curves is very important in constrained optimization, because the solution, some of you may already know that, the solution lies at the tangency between one of these level curves with the budget line, okay? And we have a unique solution in most cases, even if our function here has positive exponents, also very large, which is not a concave function, but it is quasi-concave, okay? You can regard quasi-concave functions as linear transformations of, as increasing transformations of a concave function. So I take this as the chance. There are many definitions of quasi-concave functions, and many of them prove to be equivalent to each other. Equivalent means that they identify the same set of functions, even if they are stated in very different ways. And one, this is an informal way to introduce them, but if I have a function f of x, f of x1, x2, xn, which is concave, and I consider this function, which is h, or maybe capital F, let me show you, capital F, which is g, it's a composite function, g of f of x, where g is strictly increasing, is a one variable function g, okay? It takes, I mean, you have n variables, put them into the machine f, you get one number, which is f, okay? It is y, let's say y, your variable. Then you put this number into function g, which is a function of one variable, and you get capital F, okay? Is strictly increasing. Then function f is quasi-concave. So this is a definition of quasi-concavity. It can be regarded as a definition of quasi-concavity. There are other definitions which can be proven mathematically that lead to the same set of functions. In other ways, a quasi-concave function, whatever is the way you define it, can be regarded as a strictly increasing transformation of a concave function, okay? Now, look at this. Suppose that you have f of x, which is concave, okay? And you obtain that the gradient at a certain point x is equal to 0. What do you conclude? You have a concave function. Just remember our past exercise. You have a concave function, compute the gradient, solve the system, and you find a point x star such that the gradient at this point is 0. All the partial derivatives are equal to 0. So what do you conclude? X is
maximum point.
Global maximum point. Now, what is the meaning of gradient, for instance, in two variable? This means that the partial derivative with respect to x1 is equal to 0, and the partial derivative with respect to x2 is equal to 0, okay? This means gradient equal to 0. Now, suppose that instead of having f of x, you have this previous slide function g of f of x, which is equal to capital F of x. So a strictly increasing transformation of our function, okay? Clear? What is the gradient of f, capital F? It is the vector of the two partial derivatives of capital F, okay? I have to apply basically, so for instance, the partial derivative of capital F with respect to x1 would be what? Partial derivative of g, call this y. Okay, call the partial derivative of g with respect to y times the partial derivative of y, which is partial derivative of f, with respect to x1, okay? And the second one would be the partial derivative of g with respect to y, where y is f of x, okay? Times the partial derivative of f with respect to x2, which is equal to 0, 0. Okay? So basically, what we see here is that we have that in the case of a strictly increasing transformation of a concave function, the fact that the gradient of the inner function is 0 implies that also the gradient of the strictly increasing transformation is 0 due to the chain rule, okay? But also another important point is that if x star is a global maximum for x, for f, what is the definition of global maximum? F of x star is greater or equal to f of x for any x in the domain, right? This is the definition of a global maximum. Now, what is g of f of x star? Which is basically capital F of x star. This will be greater or equal to capital F of x that is to g of f of x, again, at any point of the domain. Okay, suppose that they have the same domain. So what is the meaning of this? If x is the global maximum for function f, it is a global maximum also for function capital F, provided that g is a strictly increasing transformation, a strictly increasing function. Why is that? Because, I mean, what is the meaning of strictly increasing function? If you take two values in the domain, and the second value is larger than the first one, also the values of the function are in the same order, okay? This is a value of the domain for g. This is another value for the domain of g. You're taking this, which is larger than this, so also its image through g, which is this one, will be larger than the image of this one through g, which is this, okay? So the order is preserved if you take a strictly increasing function, okay? So in the maximum problem, in a maximization problem, you can focus on the inner function, provided that the outer function is a strictly increasing transformation, okay? Or for instance, let me see if I can find an example here, which is, if you look at the previous example in the previous slides, the log of 1 plus alpha x minus beta x was concave, remember, and has a unique maximum, okay? Now, suppose that you have this function, exponential next you can simplify this, of course, plus this is a strictly increasing transformation of this quantity. It is the exponential of, okay, plus cubic power of. These are two strictly increasing transformations. We don't need. Once we recognize that this is a strictly increasing transformation of this, we can go back to the inner function and just maximize the inner function, and our result will be the maximum also to this one. Okay? But this is not concave. This is concave, this is not concave. Okay. Can you see the point? So if you have a strictly increasing transformation of some quantity, don't try to maximize the whole function. Just go to the inner function, okay? Try to maximize this, and the maximum point for this function will be also the maximum point for a strictly increasing transformation of that function, okay? So basically, this is a digression just to show you that in principle we can go back to the simplest, the problem in its simplest form, okay? Maybe that example was too complicated. There are easier examples, but of course. If you have, okay, that's okay. I will see. You will see more when we have specific examples. Anyway, in this case, we have that whatever the sum of the exponents is, the level set is a set of convex curves like this for the Cobb-Douglas function. So what are implicit functions, and why we do need a theory for them? And we need a theory to be able to compute the derivatives along a level curve. Just because in this case it is easy to make y explicit with respect to x, but in some cases we cannot do that. Okay? So for instance, If you look at this example, look at this example. Exponential of x squared y minus 3x minus 2y equal to c, or exponential of x squared y minus 3x minus 2y minus c equal to 0. You have a mathematical expression in two variables, and you have equal to 0, okay? There is no way to make y explicit as a function of x. And there is no way to make x explicit as a function of y, okay? Anyway, this is a curve in the plane, which may or may not define a function near a given point of interest. So what is the problem here? The problem is that an expression like that one could define a curve in the plane like this, and this is a function. What is the idea behind the concept of function? For any value of the domain, you have a unique, for any value of x, you have a unique value for y, okay? But it could define a curve in the plane like this, which is not a function as considered globally, because that's not true that for any value taken in the set A for variable x, you have a unique value for y. For instance, here, you take a value here, you have a unique value for y. Here, you have a unique value for y, but there is a wide range. If you take a point here, you have 1, 2, 3 values for y, okay? So this is not a function. But this kind of expressions, f of xy equal to 0, could define this, this, or this. So a big problem is understanding when, whether, at least near some point of interest of this curve, there is at least locally a function, okay? We must be sure that at least locally there is a function and not something different. So this is not a function. This is, of course, this is the same as before. This is not a function as considered globally, but suppose that I'm interested in this point and what happens locally around this point. Locally near this point, I do have a function, okay? Suppose that I'm here in the graph. I'm really interested in what happens locally around this point here. Locally, there is a function. What are the only points of this graph where there is no way locally to have a function? Locally means even taking a very, very small circle, including the point. There are the 2 points with the vertical tangent, okay? One is this one, and one is this one. If you have this point, the red one, you can take even a very, very small circle around this point, but you will always have something similar to this. So something that bends backward, okay? So here you don't have a function near this point locally. Near this point locally, this one, you don't have a function. But for any other point of this graph, you do have a function locally, okay? Is that intuitive enough? No? Okay, let me show you this one, and then I try to enlarge. Okay? Can you see that? Is that difficult? So with implicit functions, with equations of the type f of xy equal to 0, one big problem is I'm interested in a given point of the graph of that two variables equation, okay, which is a curve in the plane. I want to know whether, at least locally, this represents a function, okay? And the other point is, if this represents a function, I want to compute the derivative of y with respect to x, even if I'm not able to express explicitly the function y is a function of x, okay? I want to compute the slope, even if I cannot express this as a one-variable function, y function of x, for which I know the differentiation rules, right? I want to know a more general rule to compute derivatives along level curves, even expressed in implicit form. So there are two problems. Well, the first problem is theoretical, because in most, these are very particular cases, so we can exclude them very quickly. But the second point, computing the derivative, is one of the most important tools needed in microeconomics, for instance, okay? Computing derivatives along level curves without worrying about making this explicit. using implicit differentiation techniques. So if you look at the graph, suppose that you have this one, x, y. And you have something like this. And this represents f of xy equal to 0. You put this into your web-based plotter, okay, and you get this, because it is computed point by point, okay? So basically, how do computers compute these curves? They fix a given level for x and solve the equation, which becomes an equation for y. They may find one solution in this case, or 3 solutions, okay? And they plot the points, and then they reconstruct the graph. Analytically, what can we do? Suppose that I'm interested in this point, okay? Can I identify, let's say, call this not a neighborhood, because this is a term, very general term used in mathematical analysis, a circle, a small circle. Can I identify a small circle surrounding this point, such that at least there, the graph of this curve represents a function? In this case, yes, because if I enlarge this, I get precisely this one, okay? It is a function there, at least locally. I can do the same here, and I can also do the same here. I use a different color. Here, locally, this is a function. Why? Because I can enlarge this, and I get my point, and locally, there is a function, okay? You see? It's this one, enlarged. Can I do the same for the 2 points? There are 2 very particular points here, having a vertical tangent. The vertical tangent is here and here. Can I do the same for these points? No, I cannot do anything similar, because if I take any circle around this point, even a very small one, I get a kind of self-similarity with respect to the macro view, okay? So I get something like this. I'm trying to enlarge this, okay? And again, I have a point with a vertical tangent, but it is not possible here, if I take a value for x in the horizontal axis, for instance here, I always have 2 values for y corresponding to this. And I can repeat this for every circle, even very small. And the reason is that this point lies at the precise point where the tangent is vertical, and my function bends backward, okay? Can you see this? And the same happens here. There's no need to enlarge this. It is the same problem. So the point here is, how can I, given this equation, how can I exclude these points with a vertical tangent, basically, okay? So to be sure that at any other point, I can, at least locally, define y as a function of x. And given this, the next problem is to compute the derivative of this y as a function of x. So this is the main issue. And there is an important theorem. So this is the question. Does this equation define implicitly y as a function of f? This is the equation, okay? Does this equation define implicitly y as a function of x, at least sufficiently near a point x0 or y0 which satisfies the equation, which means at least in a circle surrounding my point of the graph? And we have one of the most important theorems, and this is stated here just for completeness. I just want you to get the intuition of this theorem and the meaning of this theorem, okay? Next time I will show you the examples. So I'm just going to present you the theorem, and next time we will work out two full examples with the partial derivatives. Then you will find this implicit function derivatives more often in constrained optimization when dealing with level curves of two variable functions, okay? Okay, so implicit function theorem, the framework, so the assumptions behind this result is that we have an equation in two variables, f of xy equal to c. If you have this, just move this to the left and you get this one, okay? This is a two variable equation. You have a point x0, y0 satisfying the equation. That is, since the point satisfies the equation, f of x0, y0 is equal to 0, okay? Because it satisfies the equation. So in our examples here, this point, x0, y0, satisfies the equation that defines this curve. So f of x0, y0 is equal to 0 because it satisfies the equation, okay? Only the points satisfying the two variable equations lie along this curve, okay? So if this point is a point of the graph, it satisfies the equation. So this means take a point on the graph of this two variable equation. Suppose that our two variable function, you look, this is a two variable function on the left, has continuous partial derivatives near this point, and that the partial derivative with respect to y at the point is different from 0. Now I am regarding only the left-hand side as a two variable function, okay? And I work, this is a derivative of a one variable function in principle because it is a curve, but I can compute it by looking at the left-hand side, which is a two variable function, okay? Suppose that the partial derivative with respect to y at the point is not 0. This condition can be proven geometrically, which is equivalent to excluding the vertical slope here, okay? Excluding the vertical slope here means assuming that the partial derivative with respect to y at the point is different from 0. Then, if these conditions are satisfied, the two variable equation f of xy equal to 0 defines implicitly a unique function y equal to f of x near our point x0, near x0 because now the domain is x, okay? I regard this as a one variable function. Y is a function of x near x0, namely f, capital F of x, capital F is this one, of x, and y, which is now regarded as a function of x, capital F of x, is equal to 0 near x0. So this is the implicit function theorem, okay? And the second part, so this is, okay, we are sure that our two variable equations, at least near this point, defines implicitly a function, y equal to f of x. Doesn't matter if we cannot express mathematically this function. We know that this is actually a function, so y is f of x, put f of x here, we can write this in this way, okay? Moreover, our function is differentiable continuously. It means it is a one variable function having the derivative, and the derivative is a continuous function itself. And how do I compute this derivative? The derivative of my function f, even if I don't have the mathematical expression of f, is given by minus the ratio between the two partial derivatives of capital F with respect to x and with respect to y, okay, at the point xy, where of course y is equal to f of x, okay? In particular, the partial derivative of this function at the point x0, that specific point of the graph, is minus the partial derivative of capital F with respect to x at the point x0, y0, okay, divided by the same partial derivative with respect to y at the point x0, y0. But this is not only limited at the point x0, y0. This is a formula for the derivative at least sufficiently close to that point. So what I mean is that in the graphs, in the above graphs, what I get is not only the derivative, so the slope at the point x0, y0, but the derivative along the graph near to that point, okay? So I have a more general formula. This may be difficult, but its application in the common case is not difficult. It's quite easy, okay? So these are some observations. In particular, I explained this already. In particular, partial derivative at the point is the same formula where the two partial derivatives are evaluated at the specific point. This is another, the assumption of the theorem is that the tangent to the graph is not vertical. So these are just observations. And also the right-hand side here, okay, you express this as the ratio between two partial derivatives of a two-variable function. This in principle depend on x and y, but in fact, this is a function of x only, because y is f of x, okay? Proven in the previous part of the theorem. So this is expressed in terms of x and y, but it is in fact a function of one variable, x, because y is regarded as a function of x. And also, we don't even need to be able to solve, this is an important observation, we don't even need to be able to solve the equation f of xy equal to 0 explicitly for variable y. We can compute the derivative without solving the equation explicitly. Okay? Now, this is one of the most common tools in microeconomics because it allows us to compute the derivatives along level curves without solving for these level curves explicitly y as a function of x. Why? Because in some cases it is easy. We could even solve it, okay, and compute the derivative directly. In some other cases it is possible, but when you solve y as a function of x, you get a very huge and expression, very difficult to handle, okay? But if you use the implicit function differentiation rule, you get much easier results and computations. And in the third case, we may be interested in a general model in which this is the level curve of a two-variable function, and we don't have the mathematical expression of this. It's a general model. We know certain properties, and we want to work out the analytical results in general, without having a specific expression. So if we don't have a specific expression for capital F, we cannot solve for capital F, okay? For y as a function of x. So we have very good reasons for finding it convenient to work with this formula rather than making y explicit as a function of x, okay? So this is the implicit function theorem, the implicit function differentiation rules. Here is an example already. You are invited to look at this example and to compute the slope, the derivative. Just try to look at this example for the next time. I will show you another example next time. I will show you how we can use this, this property very fruitfully in practice. And also in the situations in which we know how to solve y as a function of x, I will show you why it is convenient to leave the expression as an implicit expression and work out the derivative implicitly, okay? I will show you why this is important. And next, these tools will be applied to constraint optimization. Implicit function differentiation theorem is basically the mathematical background behind the main result in constraint optimization theory, which is the use of the Lagrangian function. Okay, so I will show you next week a little bit of theory and many examples on constraint optimization. And this will close the first part of the course. Next week we have 2 plus 2, right? Four more hours. Do we have 4 more hours? Yeah.
More hours?
No, I mean, 3 plus 3, 6 hours, okay? So that's enough. We have 2 days, 2 more days, okay, 6 hours. That's enough to also to have 2 or more hours for to recap things and to make some review exercises, okay?
So with 2 hours, you're gonna end the first module, right?
Sorry?
With just 2 hours, you're gonna end the first module.
In 2 days, we're going to hand the first module, okay? 2 days classes, okay? 3 plus 3 hours. And my intention is to leave at least 2 hours to for review exercises. But you should expect in the exam exercises that are structurally very similar to the examples that we solved here. Okay? Structurally very similar. Because these are examples that are very, very common. So I would like you to be able to understand very well the structure of these examples and solve similar ones. So just look at the slides, and by the end of the next week, maybe also this weekend, I will put on the website the list of exercises that I regard as very similar to these ones. So useful as extra exercises. Okay. See you next week, and have a nice weekend. Bye.
Thank you, you too.
Bye,
Bye.
thank you.
Bye.